Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right. So hopefully you're enjoying this. Because I've been to many, I know as students, it's great you're pretty used to people giving you lectures and you're listening to lectures and writing notes, and I don't want you to do that. I have done a lot of reflection in my life about education here, education in the US, education elsewhere in the world, and I sort of have come to this conclusion that, and this is not a unique thing to me, I mean many people will tell you exactly the same thing, but I have the opportunity to implement that a little bit. And so what I want you to do is, I just want you to be motivated, and I want you to understand what is it that we are trying to do, and you understand that where are the sources of information that you can get. I can't do justice. So I'm not, for example, Kyle gave you this talk about, what did he talk about? Localization, right? Localization, and Kuhn gave you the Sora. So they were, in some sense, teaching you about very specific technologies that you can use for on bigger systems, like and what they did, how they solved the problem. I wanted to have a departure from that. I wanted to sort of give you sort of the bigger picture of all this stuff, and then motivate you to go back and look at, for example, Sora, and then how you can use that platform here. How you could potentially use array tracking for localization. Now it is for indoors, but potentially there's a way to do it. How you could use full duplex radios to improve some of these systems as well, right? So that's why I said, hopefully you'll enjoy this more than just sort of writing notes. But let's do some technical stuff too, because otherwise you'll just say, I just heard fluff stuff. So it's not fluff. All right. On that note, let's start with another video. This is kind of a repeat of that, and the point that this video made is actually the only reason I'm showing it to you, because I like the guy who's going to speak in the background. Let's see if you can, if you're a movie fan, you will know exactly who it is. If you're not a movie fan, it wouldn't matter. You had a question before I start? No, so the network operator has to. So for example, whoever's managing the network here, for example, right? They, for example, if they provide access points and you connect to the access points, the access point is responsible for that, not every client. That's how the system's going to build, because it'll be too much of a burden on the client if every client has to do that. So even the access point, you can come up with some interesting solutions. Those are open problems. Now, whatever I say in that thing is not written in sort of concrete. This is something that you can design and see what you can get away with given the rules that are provided to you. Okay, let's do, yeah. So yeah, I guess the point I didn't make earlier, the point I was saying was that about education here, there, etc., is that what I wanted to is research is one of those beasts which is not, like every problem is not a solved problem, and that's what I wanted to appreciate, which is that when you go to undergraduate or whatever, you read books, you learn the concepts, the theory, then questions are given to you, and we test whether you actually understood everything. That's actually necessary, absolutely necessary. But when you transition into the research world, you're sort of, it's an ambiguous situation. You're not very clear. It's not, no solution is the perfect solution. Sometimes you don't even have solutions, and that's what I wanted you to appreciate. Which, like, a lot of the things I'm telling you is, I'm telling you what are facts, and then I'm also leaving you with some open-ended things, so for you to say, oh, this is where the opportunity is, and then also wanted to tell you about some commercial opportunities as well as research opportunities, and there'll be more of that here. So let me just start with this video, which is kind of a cool video, but let's see.
What if you could better educate children living in a remote village who lack access to specialized instruction? What if you could manage traffic, so gridlock doesn't stop your city during rush hour? What if you could provide state-of-the-art high-tech medical care to people living in remote communities? What if governments could use technology to better deploy city services, such as garbage removal, and reduce costs in the process? What if a boy who dreams of playing in the Premier Leagues could finally stream his favorite team's games? If you look for the answers, you won't find them in what's out there. But you might find them in what's not there. It's called white space, and it's a renewable natural resource found in unused radio frequencies. These unused white space frequencies can be used to increase available bandwidth, improving the quality of broadband connectivity. And lots of these unused frequencies are located between TV channels. Signals sent out on these unused TV frequencies travel far and penetrate trees, walls, and other solid objects, inexpensively extending the reach of Wi-Fi and other wireless broadband technologies currently limited to using higher frequencies. What can TV white spaces enable? You can manage traffic in your city minute to minute, adapting the infrastructure to accommodate conditions. You can more efficiently deliver public services. You can have medical resources be available for preventive care. By reducing the cost of broadband connectivity, a school can now become part of the global village. The only thing stopping this from happening is the lack of favorable, consistent regulations allowing white space technology to be deployed on an unlicensed or license-exempt basis. People and the devices they use will finally be better connected by tapping into the TV white space available in your country.
All right, so first of all, does anybody recognize the voice? There you go. So you have fans. He's a great. I like the video just because of that, because I think he's speaking very well. But there is a point to the video. The 2 points are, one, the different scenarios that you can implement, and the second is that you need worldwide harmonization. So somebody asked me the question in the break that what's preventing India, for example, to implement this. One of the things that is preventing in India is there's no harmonization. There is no concerted effort here to kind of think very hard, deeply into this. And when I made the earlier comment about leapfrogging, I think that is how you have to think. You have to think that look at the future, look at these technologies, and say the way to do it is while the world is struggling, you know, India, we can actually leapfrog and do much more, but that does require regulation and movement forward. And generally, if you have harmonization across the world, then products will get built, because then there's more commercial opportunity. When there's more commercial opportunities, there'll be more of these things built, and when they're built, then you will have more these scenarios that we've talked about are something that you can implement, and people can both benefit financially from it plus usefully. So there was some point to that video. Okay, now let me start with a question that was asked also at the intermission. It's a movie. Anyway, about is it just like these TV white spaces? So there was this thing called the PCAST. PCAST stands for Presidential Commission on Advanced Strategy and Technology. So this is a body of people that are appointed by the President of the United States to think about the future for technology inside the U.S. to keep U.S. competitive with the rest of the world, or even ahead of the rest of the world. Because a lot of the gains in the U.S. is because of the money, and the money comes because, believe it or not, because of the technology. The technology front has been enormous for the United States. So these guys went and did a lot. So they were the who's who of the tech world. They were not technical leaders, but they were business leaders. So they were sort of CTOs of Google, CTO of Microsoft, top of big company, multi-billion-dollar companies come together, and they tapped into their internal technical guys. Like, for example, I was asked questions to write a report, and they wrote a huge report. But inside the report, they said the norm for spectrum use should be sharing, not exclusivity. This is exactly the point that I started with my first slide in the first lecture, which was to say that this the thing about separating the spectrum and exclusively giving it to somebody is gone. It's not the future. The future has to be about sharing, and that's what they came to themselves, and sort of said, if we can get this done, then we can multiply the effective capacity by a factor of 1,000. Okay, which is pretty large. Now, so the question that was asked in the mention was, Is it only about white spaces? No, white space is the first manifestation of the dynamic spectrum access concept or the opportunistic network. So if we get it right, then we can argue and try to open up the other bands as well. Now there's a large project that I'm also involved with, and that actually Krishna was quite a pioneer in India who did it too, which is around spectrum observatory. This is about, if you read literature, if you read newspapers, you will see that people say, oh, we have a spectrum crunch, we don't have a spectrum crunch, oh, we have enough spectrum, oh, we don't have. So all this debate is all BS. What we need as scientists is we need hard evidence. We need evidence of whether something is happening or not. So what you do is you create an observatory. You create a way to observe the spectrum across the entire bands, and that's your ground truth. That nobody can argue with, because if somebody says it's being used, you say, nope, last 6 months we've been looking at it, nobody's using it. Or somebody says, well, it's not being used, sorry, it actually is being. So you need that kind of an evidence. So I said Krishna actually built a system like that, and in a sort of a distributed manner, which you could just put your spectrum analyzer and then tap into this large system, and you can observe. And so we have taken it in Microsoft, we've taken it to the next level now. We are building this all up, and so we are going to go beyond white spaces, but we have to succeed in white spaces. Without success, we can't go to the next thing. And if we succeed in white spaces and go beyond, then we can get to the dream, which is that everything is shared, nothing is exclusive. All right? So much says that. Now, another question came up, and obviously these were not planned. I expected these questions, so I have these slides. So another question comes up, what about leasing? So the idea of leasing, if you don't know what was meant, was that let's say the cellular guy has this spectrum that has been sold to it, and what if you lease it? Like he says that I have the spectrum in this rural area, but nobody is using it, but I own it. You can lease it from me for a certain amount of money, just like you lease cars, you lease homes, you lease whatever. And then you, after you lease it, you kind of use it, right? So if you are interested in that, there is a lot of stuff. There's DICEPAN as a conference. Whenever I have this black box with a thing, I'm referring to some paper that was published in DICEPAN in 2005. I have references at the very end that you can look at. Obviously, I picked only, well, not obviously, but I picked ones that I was very familiar with and easy for me to do. So these are in some of the papers that I've written, but this is a pointer which will lead to more pointers in some sense. So that's where the conference 2005, we talked a little bit about that. The thing we've been talking about is opportunistic, which is different in contrast to leasing, is like these guys are talking, and when they're not talking, you sense it and then you use it. Okay, so that was also published in DICEPAN, and this was an earlier paper and some earlier ideas in it. Now let me say something about leasing. How is leasing technically going to work if you were to design a system? Now, these are again open problems. Researchers are just working on them, and nothing has been really moved to the point of any commercial thing. So really what you need is, when do you want to start, when do you want to end, what's the center frequency, what's the band, and how much power you want to operate on. Ready? Right? That's what you need. So you can then create a protocol like DHCP in the internet. You call it, let's say, DSAP. Dynamic Spectrum Access Protocol, right? You sort of say, some entity somewhere will take this request from you, and decide whether it can offer you something. And it'll offer you something. Now that entity, especially the guy who owns a spectrum, let's say that entity puts it up, they're going to say okay, so Ram is asking for something. He's asking for some center frequency with some bandwidth, and Kun, who's reading his laptop, is actually looking for that. I'm sorry. But he's asking for something as well. But he's asking for center frequency, which is slightly different, bandwidth, which is a little bit different, power is different. Now, I have to decide here what is more profitable for me, who to give it to, right? Because whoever I give it to, the other part of the frequency is now sort of fragmented, and I can only give to somebody else because once I've given it to that individual or into that client. So this is a serious theory problem here, right? Because you're trying to maximize utilization and maximize profitability, however you design it. I'm not going to say more about it, but there's a lot you can say here, and there's a lot of work in other fields that you can bring here to solve this. You had a question? Yeah.
Can't we have a lease priority? Like, for example, we are selling spectrum to certain regulator, some operators, for example. So So now instead of selling it to an operator, you give him a priority superior to the others, and for that you have some monetary exchange or something.
Yeah, you can. This totally depends. That's why I say, yes, you can have that priority based on your commercial interest. You can also have a fairness thing that I'm just going to be fair to whoever, or you can be first come first serve. You can come up with anything. So it really depends on what your own priority is. What is it that you're trying to optimize against? Okay, so you can decide on that, and you can build a system based on those decisions. And so,
there can be a bargaining solution to this also, that
yes.
people can come up with a bargain.
Yeah.
How much spectrum can be given to one and how much can be given to one.
That's right. That's auctioning, or bargaining, real-time auctioning. That's what happens in ads, for example, when you do search. When if you're doing search, like you want to shoot an ad for your travel. I'm looking for travel. You want to shoot me. She wants to shoot me. Then, the system will sort of do a miniature auctioning and then decide what ad to put, right? Because you both want it. So yeah, you can build systems like that. That's correct. There's lots of opportunity, lots of interesting things one can do. They can bring from the other field to do that. Then the other question was, I don't know who asked. I think Krishna asked this thing about enforcement. So once you've given it out, how are you going to ensure that the guy is actually adhering to the power that he set? Because if you have the monetary thing, which is like, oh, for this power you have to pay so much money, then what if I just give you, say, hey, I want to go at something lower but go higher because higher gives me more range. How are you going to enforce it, right? So then you think this is not an easy problem at all to enforce it. Somebody asked about the FCC, and my answer was FCC sort of has this thing truck, but commercial companies may not have this sort of a law type of thing. I don't know if you know this or not. Well, you probably don't know this. I'm going to say something bad about me. So when you go, at least in the US, when you go park in these private lots, and you sometimes park and they send you this thing, and let's say you haven't paid money, they'll send you this thing, right? If you don't pay, we'll take you to court, we'll do this, we'll do that, whatever, right? If you don't do anything, they actually don't have too much legal ramifications, legal way to do anything. They just scare the heck out of you and you immediately pay. So really think about it. I mean, somebody might prove me wrong, but really my point is when you're a commercial entity, it's not necessarily, you don't have the SEC or government hand. So you have to come up with a better system. You might want to put some sensors in the field, and the sensors are all the time, especially in the areas that you are. So you might want to invest in that sensor that provide you real-time coverage, because if you provide real-time coverage, you can immediately shut somebody down and say, you're not doing it, or you can sort of figure things out. So there's a very, very ripe and interesting area. This is an interesting area. This is an interesting area. There was, if you look at the paper, there's a paper on DSAP that I wrote, I think in 2005. You can look at it. It'll give you some ideas of what to do, and there's a lot to be done. I haven't done much work here, but there's a lot to be done here, and this is becoming hot now. Going back to the opportunistic part, really what you need is sensing. Now, what I haven't talked so far about is I just talked about databases. Now I'm talking about research and technical things. So really, let's go back to the sensing problem, right? So you've got this guy sees this kind of spectrum, this guy sees this kind of spectrum. They identify that this is the one that is available, and they communicate on this. So you need the ability to, of course, sense, and then you need the ability to communicate which one that you are seeing. Now, it may turn out that what he's seeing versus what he's seeing in terms of his sensing ability is different. Yeah, totally different, because first of all, for these white spaces, because the range is very large, so think of the hidden terminal problem in Wi-Fi. That's exasperated in some of this, because this is a lot longer, a lot bigger. So you can have that issue. Now you have to have this hardware. I've alluded to this, which can now change the channel, right? We wrote a paper which I think of as a landmark paper, which is to say, we question this thing about in Wi-Fi, why do we have 20 megahertz? Like if you think about it, many people, so that's what I think about, like for example, in books will teach you Wi-Fi has 20 megahertz channel, you'll accept it and you do all kinds of calculations. But you have to ask the question, why the heck do we need 20 megahertz? Why did 20 megahertz, why did they decide with that? Then if you ask the question, then you say, well, let me see, can you do better than 5? Can you do better than 2? Not everything needs 20 megahertz, right? And then you start to realize that, yeah, of course, you can do better. It's got different properties, you can do more. Then you say, well, can we design hardware towards that? And of course, you can design hardware towards that. Now so we wrote that paper, by the way, it was in SIGCOMM published. But that paper was really, honestly, motivated from white spaces stuff. Because in white spaces, we didn't have 20 megahertz, we had 6 megahertz. And so we had to design systems which could operate in 6 megahertz, and then we had to have the ability to sort of move them back and forth. And so when we were doing it there, and we say it works for white space, why the heck doesn't it work for Wi-Fi? And so that's how we moved. But anyway, you need hardware with channel adjust and frequency this thing. Okay, and then because you're going to switch channels often, because primary users are going to come, you need this overhead of switching channels to be much faster. And you can do that. Initially, there was a time when it used to take 25 milliseconds and even 50 milliseconds. Now we've gotten it to 80 microseconds. And so there has been some work there as well. Another thing is this about the sensing. So the thing that I didn't say, I mean, I sort of said it in the questions and answers, but let me show you with some real thing. So there is this thing about microphones. Now microphones occupy 200 kilohertz. Now there was a big microphone lobby, which I'm not going to say much about, but very powerful lobby, which said that you cannot operate because we use microphones. Like, for example, big games, cricket matches, or football matches, or anything like that, we're using microphones in that particular band. So the question is that they had the power to go and tell the database, you can't use this channel. So 6 megahertz was gone because 200 kilohertz had to be used. That's just ridiculous from a technical perspective. So what we do is we build this thing. This is an anechoic chamber. I don't know if you know what an anechoic chamber is, but essentially it controls the propagation of radio waves. So you can't get in, you can't get out. And it's very, very clean. And so there's no interference, nothing. So inside the anechoic chamber, we put, like, this is a mic, and we recorded something. I'm going to tell you what the original thing is. Then what I'm going to do is I'm going to actually start doing white space transmission in that same frequency band. And I'm going to tell you how that recording feels like. Okay? So let's do that real quickly.
She had your dark suit and greasy
So
wash
this is
water
the
all
original
year.
recording. Right? So we
Don't ask me to carry an oily rag like that.
nothing is happening at this point. It's just purely just recording it. Okay. Now I'm going to play with white space transmissions going on, the same band.
She had your dark suit and greasy wash water all year.
Okay,
Don't ask me to carry an oily...
No, I don't want to play that. I want to play this. So what happens when you're transmitting? Okay?
She had your dark suit and greasy wash water all year. Don't ask me to
So
carry
you're hearing
an
that,
oily
right?
rag
You're
like
still
that.
hearing the recording, but this is what happens when you're transmitting also. Video. And then if you do subcarrier suppression, which is what I showed you, adding with the notch filter here, then the same thing is this. And this is with this. So you got a notch at 200 kilohertz.
She had your dark suit and greasy wash water all year.
That's it. It's not
Don't
big.
ask me to carry an oily rag like that.
All right. So what I wanted to show was some original recording, and then I wanted to show you what happens when white space transmission was happening. And in the original, you could hear, and you have to take my word for it, and we'll try to do it later to see if it works. You could hear it very clearly, the thing, of course, because it's original. And then when we did the white space and then we recorded it, it was garbage, complete garbage. You could, if you really heard very carefully, you could hear the recording a little bit, somebody speaking in the back end, but it was just white noise. You know, if you ever heard like shh, that kind of thing. Anyway, so then technically you can say, well, I can solve this problem. Okay, what I can do is, so what we did is we got these two devices. There's a spectrum analyzer, and what we did is we found out where that transmission was happening in the 6 megahertz. And we built a notch filter. So essentially, you can see the transmission was happening here in this little piece. And so we built a filter which will just utilize this part and this part for transmission in the 6 megahertz channel and not do anything here, right? And then we did the same experiment. And of course, it was perfect. No problem. We could transmit on white spaces a full video while this recording was happening in there. So that told us that there is a technical solution to this problem of not wasting 6 megahertz. Now, in the real world, in the FCC world, none of this is now specified because, again, they don't necessarily yet know. There hasn't been enough push on them that you're wasting this bandwidth, because at this point, they're even trying to get systems to work in just the average thing. So this is sort of like, you can think about the next generation of technology where we can actually sense something, do the right thing, and still be able to utilize a lot of the bandwidth. I wish I could have shown you the thing. It's very dramatic, but that's okay. Just believe it. So now I'm going to show you something we built a long time back. And again, just to give you a sense of what you need to do to build that. So we took a 2.4 gigahertz Wi-Fi device, and we made it work in the 6 megahertz. So we took a Wi-Fi card, we added mixture to it with a wideband synthesizer, some TR switch, low power amplitude, 6 megahertz band pass filter, a TR switch, and then we sort of brought it back. And so really we took a Wi-Fi system and we converted, so a Wi-Fi card, and we converted it into a 6 megahertz with some very, very simple components in there. Okay. Now, and we built this. This is what we sent to the FCC when we were trying to prove to them that you can build something. So this is a laptop. This is the radio. It looks kind of crummy. It could scan from 400 megahertz to 928 megahertz and 5 megahertz channels. It could dynamically adjust the channel width and center frequencies. And we could just show this thing. So it was very simple. I honestly believe two seniors can potentially get in the lab and build something like that. So again, this is to remove any things from your head that this we actually have to go and buy this expensive hardware. You don't. You can build this. Now, from a networking perspective, there are lots of interesting questions to ask. All right. First question is, how should these nodes connect? Now, I'm moving away from the database. I'm now moving to the technical world where I'm going to say, and even in database, some of these things apply, but I'm saying I really want to build a system that can sense. Because if it can sense, then I can, for example, the whole reason for showing you that thing about microphone was that if I could sense the microphone, I could still transmit and use the bandwidth, use the channel without having to worry about it. But if I sense, then how do I know that what I'm seeing is exactly something the other node is seeing, because he's pretty far away. So how do we connect? How should I even discover that these nodes exist? Because this is not like a Wi-Fi system anymore, right? It's not like, then which subband should the two, this I sort of talked about, center frequency channel, etc. How should these network group react when some primary user shows up? Now, if primary user shows up in node A and B can't listen to it, A has to change, but has to somehow tell B that you have to go to a different channel. So how do you do that? And then what kind of protocols do they use? Can we actually do these protocols? Do they even exist in the real world? And then the question is, what are the tools that we need to build to be able to say something scientific about these things so that we can actually give some properties to any of this stuff? So really, as you think about this, network is a little different from what we've done in the past. So I'm going to show you an attempt at this, first attempt. I'm not going to say this is not the most exclusive, this is not cast in stone. There are many new interesting things, and if you sort of come up with interesting new ideas, then more power to you. You should design it. But this is an attempt that we made. So think about this as a multi-radio architecture we actually had in this first instance. We had a scanning radio, which was scanning the channels all the time, and then we had a transmitting radio, which could sort of reconfigure the channels, right? So that was the property of the hardware that we built. Now, we designed a new MAC protocol. We designed a spectrum allocation. I'm going to talk a little bit about this, and a resource allocation matrix to be able to take advantage of that. So this was a control channel based protocol. So instead of Wi-Fi, where we have sort of the control and data are mixed in the same plane, right? We have RTS, CTS, and the Wi-Fi. We actually separated the two out. So in the control channel, we were able to use for contending spectrum access, and this was also used to sort of understand what the spectrum looked like from where you were watching it. And we called it time spectrum blocks, and you will see why I call it TSP, the time spectral blocks later. And then we have this allocation and reservation engine, which is, again, I'll tell you more details about it, but really this was to give you a full picture of everything that is happening around you so that you could figure out where you want to transmit. Again, this is a very, very flexible system that we are trying to build here, okay, generated 2D view of it. This all has to be distributed, no centralized thing. That was a property. So what does the MAC protocol look like? So we try to take advantage of what we already know. We know about RTS, CTS. So RTS would be sent to indicate that I want to send to you, to node B or whatever. And it'll include the different frequency or time spectrum blocks, which are defined as, again, I defined in a few seconds, as this is the frequency I want to operate on and for this long. Okay, so you send it. Then the CTS will send you the reaction saying, hey, I see it too, or I don't see it. These are the ones I see it. So it can be an array, or it can be just one TSP. So it tells you, the frequencies, and then if there's a sort of a match, and hopefully there is a match, he says, this is the one that you can operate on. These are the 3 ones that I think. You can prioritize them. You can do whatever. You can say, this is the best one, and you can decide why that is the best one. This is next. And then you say, introduce this new thing called DTS, which is not there in Wi-Fi, and say, okay, fine, let's agree on this one, and I will transmit to you in this particular TSP. Okay, and then you sort of do that, and then you wait for just a few microseconds or whatever, and then you do the transmissions in the TSB, in that time duration spectrum location. She'll tell you a little bit more about it in a second. So, pictorially, this sort of looks like this. So you have time, you have TV bands. This is sort of transmission that are going on. So your time spectrum blocks looks like this is the size of the frequencies. This is the amount of time I want to use to send it, and it sort of sits. You can sort of sense if you've got sensors or a sensing channel. You can say this is the time I want to use your channel on. And then everybody else, all the nodes do the same sort of things. This color indicates different things, and they reserve the channels and they transmit the channel. Now inside the TSB, you can use whatever MAC protocol. I mean, this is a MAC protocol, but you can use another MAC protocol. So if you want to sort of use something as simple as I don't know what happened to my animation here. Actually, I had a transmit act. That animation is gone. But you can inside the TSB you can use whatever mechanisms you want. If you want to do, I'll send you a packet, send me an ACK, send me a packet, send me an ACK, that you can do that. Or you can send 10 packets, you send me an ACK. Or you can sort of come up with something even more fancier, because this TSB could be not just one node, it could be an entire network. So you have a lot of flexibility in here, but this is how the spectrum looks like. Now, there is this thing called the BSmart, or the resource manager. Now, the thing is, the question to ask for yourself would be that how do I decide what the size of this thing is, right? Because I could just take the whole size. That's not very smart. So what we're going to do is we're going to do a very simple thing. We're going to assign the size based on number of flows, okay? So if n is the number of flows and b is the available bandwidth, then you basically say that I'm going to be b over n, to be fair. This is designed for fairness, okay? And so choose the optimal duration for delta t. That's supposed to be delta, by the way. So now keep in mind as you design this that long blocks means higher delays, right? If you sort of have if you're using this for a long time, then everybody else is waiting, and that's not good. And then if you have short blocks, then that means that it can be too much of this contention going on, and that's not good too. So you have to come up with some optimal way of doing this. And of course, again, you can start to now apply a lot of theory, a lot of intelligence into any of this stuff as well. I know I'm going fast. I want to just finish up this thing and we can do some Q&A. So, this example of this is, for example, if you have 8 backlogs, 8 flows that you want to deal. So when the first guy shows up, he just decides whatever he decides. N is equal to 1, B over N, picks up, decides. Second guy shows up, he decides whatever this is right, T and B, and then he picks that as well because he's got all his frequencies shown up. Third guy shows up, he has enough, he can do it. But as these guys start to show up, you can start to see that the number of flows are changing. Now, one question should have come to mind is how are they knowing the flow? Remember, I had the second radio which was scanning. That radio is listening to the control channel and seeing what's going on. So everything is happening in the control channel. So even if 2 guys are talking to one another, it knows that those 2 guys are starting, and it's creating a map in itself. So it knows how many flows are going on. And that feeds into the BSmart thing, and so this is how you do. So you end up in a fair allocation as the number of flows keep coming, and then you sort of reduce the TSB size and try to do the right thing. So this is not so different from the previous set of protocols, but this is kind of how it works. So this is an animation of that a little bit as the different flows are coming in. Same thing, it just allocates differently based on it. Let me see what I... So the difference that we did here was we have a control channel protocol which is different. It's kind of like 802.11 like. The data transmission is happening on the UHF frequencies, and then you're actually creating some congestion resolution thing as well. So so again, going back just to sort of recap, the BSmart determines the size of the TSP to map the app request available. The resource allocation matrix keeps track of what is going on across the entire thing, and the CMAC actually does the transmission. So this is what we sort of created based on these 2 guys. Now, so this is all fine and dandy. It works. We built it. It works. But a lot of the people said, hey, and this is where again the practical stuff comes in. Somebody says, I can't afford to put another radio here. Believe it or not, it costs money, and I'm not making any money on this stuff. Can you do it in one radio? That was the first question. So if I give you this problem, and then you will say, okay, let me try to design the whole thing in one radio. Because we designed it from what we thought was practical, optimal in some respect. It works, everything good. So the business, I wrote it as a business question. So the question was, can we use a single radio system? And more specifically, can we use Wi-Fi? And the reason is because they say we have already invested millions of dollars in building Wi-Fi. It works really well. Can we just not use Wi-Fi instead of using this new radio that you're designing with new control channel and new TSPs and all that other stuff? So that was the problem given to us. So first we had to sort of think about what is different about our network or about white spaces that is not in Wi-Fi. So we have to deal with spatial variation, we have to deal with temporal variation, and we have to deal with spectrum fragmentation. And these are different. We also need a way for doing fast AP discovery across 180 megahertz. Now in Wi-Fi you don't require that, right? You just you're set on a channel and you operate on that channel and you're done. Because we have this notion of primary, secondary users, if a primary user shows up, you have to immediately scan and figure out where the heck I should operate, because I can't operate in the, and if you've got 180 megahertz, in theory, that you have to scan, that's a long time. And your communication is completely busted. You're not going to be able to do any video, nothing, because of its scanning. So you have to design a system which can do this very, very fast. Okay. You have to be sort of make sure that you keep the distribution. You don't actually change. You still have to not sort of worry about the primary users. Now in Wi-Fi it didn't matter because you were all secondary users per se or primary users, and so everybody had a thing. Here you don't have. So there are differences between Wi-Fi and what the system is, and that's what makes the problem intellectually interesting. Okay. So so the question, then we did this. I mean, you can there's a paper that got the best paper award at SICOM 2009 on this. You can read the details of it. But we eliminated the control channel, and I'll tell you a little bit about that paper, not the whole thing. But we came up with a spectrum assignment algorithm, a discovery protocol, and a fast recovery after disconnection to solve a lot of these problems that I mentioned to you. And so what I'm going to do is I am actually going to focus on this one because not enough time, but I've given you a reference. You should read that paper if you haven't already done it. So let's see. Let's talk about variable channels. So the first level of question is, one level of question is what, channel width. I've been saying for a long time now that channel width is no longer constant. I talked about a 20 megahertz. In this case, I talked about 6 megahertz. You want to use as much as you can, right? So it could be 12, it could be 18, it could be 24, and so we are going to allow that, right? So we're going to allow all of that stuff. And so how are we going to first find an access point which is operating? First, we have to find what channel the access point is operating on when we first connect. And then we have to find out what width it's using, right? It's a non-trivial problem if you think about it, because nothing is fixed now. We are trying to be adaptive. So I'm going to take that problem on head on. So again, some assumptions that we were making at the time. This is right after the paper and the things we did. And so this was 4 years ago, almost 5 now. But so things have changed, but not so much. So we had this sort of a PC thing. We had a connection manager. We have a Wi-Fi substrate, UHF translation, all this other stuff. Not that important. The most important thing is this algorithm called SIFT that we designed. And the innovation here was to look at the signal do a temporal analysis of the signal. Instead of taking a Fourier transform and doing analysis on that, we wanted to be fast. So what we wanted to do is we just wanted to take the samples and see, can we, just looking at the sample, can we say what width it is on? So the first question for us was to just run everything on different channel widths and visually see what they look like. So this picture may not come out very well, but let me show you. You see these 3 pictures, right? And you see that they are different, correct? And what this is if I'm trying to remember now, this is when something is operating on 20 megahertz, this is when it's operating on 10 megahertz, and this is when it's operating on 5 megahertz. Just by visually looking at it, you can see there is difference. Now, can I take that and convert it to computer reason? In the sense, can the system now my system look at this, take these samples, and just by looking at a sample tell? And the answer is yes, right? So that was the innovation. The innovation was just sample the thing really, really quickly, and you will know what width is being used, because it has to match to some finite number of widths. Of course, you can't. It's not like continuous. All right. So now, how are you going to use it? So now, let's say you can do this very fast, which we can. How are we going to use it? Now, in this case, I've divided this to show you an example. I'm saying these are all channels, these little things, right? And the access point is operating on some channel here, and it's pretty large. Okay, this is the, let's say, 6 megahertz or whatever the width is. This can be generalized to whatever number you want. This is the ones that you can't use. So how would you use it? The simple way is you kind of go and check if there is any signal in any of these, right? And then you kind of, what you do is you say there's no signal here, so access point can't be here, can't be here, can't be here, can't be here, can't be here. Then, you know, and when you see the access point, you have some signal, but it's noise because you really can't match it. So what you're going to do is you're going to change your width, and I'm going to run it again and show you. So you're running at 6 megahertz and kind of checking. You go up here too, you see there's some noise, but you didn't really know. So now you change the width, and you keep changing the width till you actually fit it to your width, and then you say, that's where the access point is. This is what you would do. This is how things work. But now, because we have SIFT and a much faster algorithm is possible, you take the same picture, and what you do is you do the same thing. But first of all, what you do is you randomize this thing. So you don't do sequentially, because all you're looking for are patterns now, just patterns, right, to see what the width is. And so the first thing is to see some signal with what width. And so you just jump around. You kind of go here, and you see, oops, I found something, right? And because you've sampled it, you know what width it is. And as soon as you have that width, you extend it to that width, and then you do the matching, and boom, you find it immediately. I know we're going fast. There's some details in here, but you can find it. So that's how it works pretty fast. So then if you do, there's some graph which says here's white spaces contiguous width. So, you know, given this is free, this is free, this is free. And then this is the discovery time. And notice that, of course, as the width contiguous width goes up, you actually do a lot better. But this is pretty fast. And here's another graph which sort of shows, I should have put another graph here to show the contrast, which I don't have, but it's pretty fast. And this is the discovery time. We try to do different version of the SIFT in different areas to detect what kind of thing is this. So we did that. Okay, I should, and let me see if I want to go through this really fast. There's a lot of words here. Essentially, what the point is, another part of the thing was that when the access point decides what channel to use, it has to sort of decide which is the best channel for it. And there's some algorithm to decide what channel, because you have many options available to you. You have to decide which option is best, and that's what it's sort of talking about. So, so this is good. So I'm sort of almost at the end here. So since the time we did all this work in 2009 and all this stuff, there have been many pieces of work that if you want to go. And the places to go to check, even this year, 2014, I just came back from this conference called Mobisis. There is a paper on white space network which talks about using it for vehicular connectivity. So it's actually a nice paper. I was reading it on the plane back and seeing whether I should incorporate it in it, but let me tell you the main idea there was the following. So they wanted to use, what the point they made is that, look, even if you have cell networks, which is what provides access to vehicles and buses and things like that, the bandwidth isn't there. So what if we use a combination of a cell network and a white space network? And so the whole paper is about saying that the cell network is the control signal, and they have to do some channel estimation for various reasons. And so they put two receivers, one in the front of the bus, one in the back of the bus. And based on what is happening, so as the bus is moving, based on what the front sees, the back adapts itself based on the channel conditions to provide you a lot better throughput without sort of failure. And they built the system in Wisconsin, and they deployed it in many buses, and it works pretty well, and that's what it was. So as you look at these conferences, you start to see use cases of this, and you start to see new problems that people have been looking at and trying to solve. And you'll start to see brand new opportunity areas for you to work in. And so I want you to look at these conferences after this. There have also been many test beds. There's one in Wisconsin. I think you guys in Houston are either building it or built it. Ashu, yeah, okay. So Cambridge I talked about, Singapore we built, Brazil we built. So there's been a lot of test beds that have been built. I mentioned it, standards have gone on, and there is lots of database providers. The other thing we learned that you should know is that I always work here, right? That's where I do, and most of you, I believe, work here as well. But you can succeed in a venture like this without actually thinking about a lot of this other stuff as well. And so what happens here is impacted by regulations without a question. So either you get involved or have these guys tell you what to do. And I suggest that you get involved and sort of make sure that it actually works in your direction, in your favor. And similarly, the businesses, this drives it, but this drives it as well. So my point is that if you're going to go down this venture and you want to do something more than just write papers and build a little system, you've got to be a lot more holistic. Or if you yourself are not, you partner with people who are to build the full, complete thing, right? So I think that's it. Yeah, I'll just leave this up. I'm on time. Open to any questions you want. Yes.
Can offloading be a solution to get the best of both worlds, that is the unlicensed man and white spaces?
What do you mean by offloading? I'm not sure.
If a person is actually, if the AP is working on the white space, only the primary appears, that can decide to offload to white spaces or to Wi-Fi. Or if Wi-Fi is not giving good capacity, it can switch to white spaces.
Yes. So you should actually do that all the time. In fact, any place where you have, so let me say two things. One is that you can do that if Wi-Fi is available there. So a lot of these scenarios that I talked about, you might not have Wi-Fi. So for example, even if you consider this campus, as you go in the middle of the campus, you might not get any Wi-Fi signal, but you'll get white space signal. So you can't really offload there. So that's part one of the question. So if you have no option, you have no option. But if you do have an option, yes, you should always offload to white space Wi-Fi, always. And the reason I say always is because Wi-Fi is a very mature and well-constructed network usually, right? And as white spaces is much more about providing range and long-range coverages. So to the extent possible, you really should use Wi-Fi, and you will probably get better bandwidth from it too. And the lesson, and this is not something new. If you think about the cellular providers, like most of these cellular providers now own hotspots, Wi-Fi hotspots all over the world, and they have software in your systems which will automatically offload to these Wi-Fi hotspots, even though they have cell coverage, because that's a very much more precious resource. So the answer is emphatic yes. If you have a chance, you should always do that. And most radios in the future are not going to be just white spaces. They're going to be multi-mode radios. Will operate at 2.4, 5 gigs, 700 megahertz. They will have the ability to do all these different things. And so then you have to write the software to do that properly. So yeah.
LTE is designed to work for different bandwidths.
Yeah.
So, but initially the client does not need to know what is the bandwidth that is supported by the base station. That is how the design is. Initially it looks at the central 72 subcarriers, and then the base station says, okay, we are using 5 megahertz or 10 or 20.
Yeah.
Can there be a similar one that is applied here? Because when you gave that example, my understanding is we are trying to determine what is the size that we are using.
Yeah.
But
That's
can
correct.
there be a similar one applicable here as well?
That's correct. So you may be right. I can't actually give you an emphatic answer here, but I do again go back to this thing about LTE is a very controlled network with a central operator with a scheduling algorithm in the base station. What we're trying to do is I designed this for AP. I gave you this example for AP, but if you wanted to construct an ad hoc network, you could still use this property that I talked about, but in LTE you can't, because LTE doesn't have that ability, although I've heard that they're now going in the direction of trying to build an ad hoc network as well. So I'll have to dig deeper into seeing how precisely LTE is done. Some of this predates those standards, I think. But yeah, so that's my answer. It's a good point, but I don't think it'll actually solve it in the more general case.
Is white spaces always point-to-point type of network? I mean, just like in Wi-Fi, the access point client, but always the examples.
Yeah. So
that was, one client and another client connecting together. I mean, there is no sort of other protocols or other things.
Yeah. So white spaces is you should think of white spaces as very similar to Wi-Fi. So it is a point-to-point thing. There is no the central thing where the access point shows up is a particular instantiation of it. So if you wanted to build a mesh network, which is just multi-hop network, you could totally do it. You could absolutely do it. And once again, because we don't, so first of all, there's a lot of opportunity to do great stuff here. So right now, the way the world has worked, and since we did all this work, has been that the standards have gone in the route of doing, if you look at the standards for white spaces, they're very similar to Wi-Fi because they're trying to reuse all the hardware, all the software, all the, not software, but a lot of the physical layer stuff. And so just like Wi-Fi has this ability to just do a distributed, it's a distributed protocol, white space inherits that distributed protocol too. There's no centralized mechanism. But, yeah, so I don't know if I answered the question.
I'm saying that Wi-Fi is also a distributed protocol. The DCF
Right.
is distributed, but here the example show that two clients are connecting with each other. There is no sort like, here we cannot think of an access point and there are so many clients that will connect to this thing because there is, these things is primary and secondary and anytime you have to switch to some other frequency. Then access point cannot connect to so many clients at a certain point. There are only two clients can perceive at the same time. So I don't think that in near future also it may be possible to do.
I see. Sorry, I misunderstood your question. Got it. I see. So let me repeat the question so you think I got it and then maybe others, it becomes clearer to others as well. So what you're asking is that there are at least two different things. One is that there is a primary user somewhere. So if he shows up, you got to switch fast. But another thing is that those access point will have a certain view of the spectrum. Those clients have a certain view of the spectrum, and then some other clients may have a certain other view of the spectrum. And so the question is, how do you compare? How do you connect to all of those things? So this is, I think, so the first part, which is the switching part when the primary user comes in, that's actually in the paper that I refer to that you should sort of read, and it takes advantage of this, which is that you can do a few things here. You can't, because you have to switch immediately, you can't, what you can't do is the simple thing, which is to tell clients, send a message saying, it's all good, because I didn't get into the details, but think hard and you'll get the details. There is a power saving mode in Wi-Fi where, right? So then if you apply the same power saving mode and the clients are sleeping, you switch and the client gets up and you're not there. So there are problems there. But in terms of solving the other thing, I don't know how to solve it in a way other than saying maybe you can put multiple radios on the access points so they can try to serve different batches of the clients based on what they're seeing and what they're not seeing. So it's a reasonable problem and there are some solutions to it. I don't want to design a solution right here in the front, but I don't think it's a not solvable problem. I just think that it requires some thinking to do that. It's a good observation, though.
Sir? Okay, let us consider a scenario in which, as we know that for broadband we can use white spaces. Now consider a scenario where there are several operators, say X, Y, Z, and they are having base stations in a geographical area. Now the question is, since there are several vendors and as we know that white space is dynamic in terms of both time and space, so if there are several users and with the same different base stations, now I want to say that, okay, my vendor wants to specify some quality of service. Like, okay, I'll be providing users with this through bandwidth or something. So this is a question that is in my mind. How will a vendor say in terms of license use also? I don't know after my license expires if I'll get a same amount of broadband and same amount of bandwidth to use or not. So how can that QoS problem be solved in this space?
So what you're asking is a question related to lease. For example, if you take the lease and then you okay. So let me first say a few words before I answer your question. So what I didn't say, and I'll take this opportunity to say now, is that there are folks, especially in the telco world, who are saying that you can run LTE protocols in white spaces, by the way. So everything I've said to you is kind of sort of like Wi-Fi based or distributed protocol. But so what they say, if you can't defeat them, you just join them. So when telcos have been trying very hard to sort of say that, well, just don't make it unlicensed, we'll make it licensed. But if they're not winning that, then they say, okay, why don't we just use LTE? Because really what they want to do is sell, right? So the reason I wanted to sort of say that is because now I'm going to try to answer your question. So the question that was asked was that if you have a leasing model, which I didn't say much about here, which is that to sort of say, so then it's not really white spaces. What it is a different model, because here the model is that I own the spectrum and I'm leasing it to you, and now you're going to provide quality of service to your clients. And your question is, what if this goes away? The lease goes away. This is a completely different model from what I'm saying, because it's no longer distributed at all. It is completely up to you how long you're going to take the lease from and how long I'm going to give you the lease for. And then based on that, you can decide what the quality of service is. Okay?
Okay, so if we consider now that so there are several base stations. Since base stations can't be owned by a simple person, so somebody needs to provide those services.
Sure.
Right? So if there are those guys, so we don't want to just sell the spectrum. So the other way is leasing. So what is the third way in distributed model? Again, there will be the problem of QoS. Don't you think so?
Okay. So let's first separate these things out. So first, let's separate the point of saying not white spaces, spectrum leasing, and that's a different problem, right? Now let's go to white spaces. White spaces, let's talk about unlicensed white spaces. In unlicensed anything, nobody owns anything, so anybody can do anything, okay? So now, even if some operator decides to put access points, it is not unlike what happens in Wi-Fi today. So an operator can put hotspots, and somebody else can put more hotspots, and somebody else can put hotspots, and there is no quality of service.
Again, then we'll be
so there is no quality of service. That's right. So in an unlicensed world, this is the biggest argument against white spaces. So one of the biggest arguments against white spaces, right? That you can't provide quality of service. It's all best effort.
So we'll again be facing the same problems as we are facing in Wi-Fi.
You will be facing in the same problem. Yes, that's not a bad problem to have, by the way, which is it becomes so popular that it's useful, because once it becomes useful, then you actually go and lobby and you create more white spaces. You make the same arguments that you made for Wi-Fi to get white spaces, and you get more things. So I think that would be great. If we have that problem, I think we have succeeded. We should tap ourselves in the back. We said we've done something great for the world. Not worry about it so much, and go after, and continue in parallel, go after more spectrum and get more spectrum free.
Hello, sir. Here's.
Okay.
Sir, I have a question about the...
You should introduce yourself so that I at least know who I'm speaking to. And
I'm Shrikant. I'm a MSY research student at IIT Hyderabad under Professor Ramamurthy, sir.
Okay.
Sir, I have a question regarding the database design.
Mm-hmm.
Before I ask my question, I just want to say something. Actually, we have attended a conference at IIT Kanpur on dynamic spectrum access for about 3 days, somewhere in October or something like that. So there were many things discussed about the technical aspects of the DSA and the policy making, bringing game theory into policy making and all such things. But for the first time, you gave us the conviction that this is all is not just a myth existing somewhere outside. As a matter of fact, all the papers, which you have published, we have read all the papers, sir. But for the first time,
it's smart guy.
It's great. It's great to see that some working model has been done. So it's I thank you for that, sir. It really encourages us.
Before you go to the next point, before you go to your actual point, let me just react and say the following thing to you, because the interesting thing about any of this is that intellectuals like to make things hard, because if it's not hard, they think they're not adding any value. So when they apply game theory, or they'll apply some interesting other mechanism to this, it's actually much more about themselves than what the reality is. So what I hope you got out of all this is that really, if you can solve the problem in a simple way, that's exactly what you need to do, because that's exactly what the world will accept, and that's exactly what every regulators will accept. So yes, in conferences you will hear all kinds of things, and they actually muddle you up a little bit, because it's just so. That's all I wanted to say, which is like, you've heard of the KISS thing, right? Keep it simple, stupid. So it's actually totally true. Okay, now go ahead. What is your point? What was your point? Unless you've forgotten it.
In fact, I was also about to forget that. So, sir, actually, while designing something like this, a database for a wireless system, did you customize that? It calls for a different set of instructions. If you design a server for typical web applications, and when you design a server and database for such applications, not many of the software things are required for this. We can optimize it to a better way. So did you employ something like that, sir?
No, so we did not, but realize that, let me just say the following, which is that we did not do a lot of the optimization that we have learned in the database world in trying to do this really well. But there's a lot of room for that. My point, I didn't want to sort of go on that angle, because that's so everything I've sort of said, I will completely submit to you that there are things you can do, potentially you can do better. Like, at least in the databases, I was sort of talking about the propagation modeling, for example, or talking about, for example, even the query mechanisms. We adopted very simple query mechanisms for it. But there has been a lot of work in the databases world which sort of gives you some regional coordinates and says, give me things around there. We didn't do any of that, and the schemas we chose were pretty simple. You can do a lot more there. I wouldn't say this is the best design. I will just say this is the way you want the database to operate.
One last thing, little bit off the way.
Yeah.
Since your discussion has been more general, I just want to have a quick comment from you on the research. Research being done in India. What do you see the fundamental difference between the research there and here? I just want to hear a quick word on you. From you.
Man, I'm going to get into trouble for this. God. Ashu. He actually keeps me honest. He actually sends me a mail afterwards and tells me. Anyway, so I will tell you what I think as honestly as I possibly can. I think that, but let me tell you my background. I also come from a systems world, so which means that if it's not clear to me, let me just say it one more time. I do not believe anything is real till I build it, until I actually can feel it, until actually it works. I don't. So with that, so I have that bias in my head. What I see, for example, in India, that ability to take the next step, to sort of take these ideas and actually build and deploy them, is just lacking. In the US, that's not the case. In fact, they have internalized this very clearly, that in most of the top universities will work hand in hand with theoreticians and build systems, practically deployable systems, and they will actually have their students. I showed you those pictures, right? This guy getting on top of a ladder and putting a lot of the stuff. This is very routine, and I don't see that here too much. So for you as students, or maybe the next generation, I think that's where you want to go. You want to sort of make things a lot more real than they are here. They have been here. I think, okay, so in the positive side, I think the fundamentals here are the best in the world. I don't think there is, like, Indians do amazingly well in US. They are superb. My group has a lot of Indians. I'm an Indian too. And they are just superb researchers. And so the cream of the crop is here. But those are the ones who have actually taken it to the next level. So as the research here goes better, and you get more money, and you deploy and you start deploying and building systems and taking all these risks, and not be afraid of failing, right? Failing is part of learning. You have to fail. If you don't fail, you're not learning. You are going to get better and better and better and better. You will actually, become top class. So I don't know if that answers the question, but generally that's the feeling I have. There's a lot more theoretical work here. That is not added to by the systems work.
Can I respond to that?
Oh, please.
So
we can get into a whole debate. Let's have a panel here. Have like Indian research.
I request you and all the members of the audience to come to a demo of some products that have come out of IISc. The demo is on Monday between 4 and 5, and you'll see some counter examples to what you.
Yeah. So let me. Okay. So I have to respond to this too. It's not about exceptions to the rule. There always are. There are people like you. There are other people I know who are very, very close friends with, who totally agree. They are either educated in the US or have something, or they are just doing. I'm talking about more general stuff, right? It's not one or two or even 1,000 people that are going to make a difference on a 1.2 billion for people thing. It has to be systemic. It has to be at the very fundamentals of what we do. So, hey, great, you're a role model. You're the torch bearer. That's great. But anyway, that's my answer. We can go more into this later if you want. Anything else? Yes.
The first thing we started the database, that was because you were not able to
Sense.
good channel sensing.
Yes.
But then again, now you have to have an MP and a client who are doing channel sensing.
Yes.
So don't you think the problem boils down to the same problem of doing a spectrum sensing?
Yes, it does. My first talk was all about. It was very factual. Everything was factual. But what I mean by factual is in that case, it was about systems that we are designing, that are becoming real, that are being deployed, all the good stuff. The second talk was about really about many open problems. And what I wanted to show you in the second talk was that I want to show you how we sort of started to go around it and how we evolved ourselves. But you're totally right. For these things to really work, you need a good sensing technology, which I actually didn't go into much, right? People like the sensing technology also has to be fast. So one of the things people have done is do energy sensing to detect. I mentioned this earlier, right? Do a threshold, see what energy levels of a signal you're getting. Then do feature extraction from them. Do pattern matching. Do some Fourier transform and then do pattern matching on that. These are all very sort of in the research stages and not really completely done yet. So yes, we have to nail that. But my demo that I couldn't really show, that would have been very dramatic had I shown you, which is that when I told you about the notch filter that we had designed to get out the microphone out, that should give you a sense of how suboptimal the real world is right now in terms of even if we were to succeed in the white spaces. And that's where all the good stuff is going to come. And that's where a lot of research will be done, plus great products will be built, right? So you are totally right. Spectrum sensing has to be done. Once you do spectrum sensing, you can eliminate the notion of databases, or you can use databases in conjunction with spectrum sensing. Actually, that's the other route that we are going in, which I didn't say much about, to use both together, where you get some hints from the database, and you then, so one example really quickly is we sort of say, the database says something is busy, but you just take it as a hint and you sort of still check. But once you know something is busy, and if it actually gives you some sense of what that is, then you know which particular signal to look for, and you look for that specific signal and say, well, it's busy, but it's not really, but let me go sense it more often because it says it's busy, so something might come up, right? So those are some of the middle ground things that you can build. We didn't talk much about sensing, but that is yet stays an open problem yet. Good questions. I like the questions.
Almost 25 minutes over.
Okay.
So I think we'll break for lunch.
Thank you. Just to give you a sense, tomorrow I'm going to talk about something that is not actually wireless. So you've been hearing wireless all the way through, right? And you're going to hear even more. But I'm going to talk about something which is in the mobile world. And hopefully it should be exciting because hopefully it should tell you where I think the next generation of cloud computing is going. So just to give you a preview of that ahead of time. All right, thanks a lot. You're a great audience.